If you want to perfectly heat a modern two-story home, the first thing you really have to do is, well, plan for failure.
Right.
Like specifically, you might need to accept a mathematical failure rate, say a 6% deficit in thermal power right in the dead center of the house, just to make the whole ecosystem work.
Yeah, it sounds crazy, but it's true.
I mean, we all tend to think of household heating as this blunt instrument, right? Like you turn the dial, the furnace kicks on, hot air blows, and you stop shivering.
Exactly. We just assume the thermostat is doing all the heavy lifting.
Right. But behind the drywall, there is this hyper-specific, fiercely debated thermodynamic war happening. And the strategies used to fight it are, they're incredibly complex.
They really are. I mean, the thermostat is just the trigger,
Yeah.
The actual intelligence is baked into the architecture itself.
Plumbing routing, the thermal mat.
Yeah, exactly. All of that is calculated long before the foundation is even poured.
And that structural intelligence is exactly our mission for this deep dive. Today we're looking at an instructional document titled Practical Exercise 3.
Sounds super thrilling, I know.
Right. But on the surface, it's a tutorial for creating a commercial proposal for an autonomous heating system in a two-story residential house. We're basically following a hypothetical engineer, the text calls him Vassel Pupkin, as he builds a virtual test subject inside this specialized HVAC software called Auditor SDG 2.0.
Right, and the test subject is a cottage located at 1 Studentska Street in the city of Rivne, Ukraine.
Yeah, and following Vassel's process through this software, it just reveals the sheer volume of variables required to build a functioning thermal model.
Oh, absolutely. I mean, this isn't just a structural layout program. It is a strictly mathematical environment.
Right.
The entire objective is to model how energy bleeds out of a structure and then engineer a localized grid to, pump that energy back in faster than winter can strip it away.
It honestly reads very much like playing a deeply technical simulation game, like The Sims, but strictly for HVAC nerds.
That is a perfect way to describe it.
Where the goal isn't to build a cool house, it's to defeat winter. But before Vasil can start routing pipes or placing radiators, he has to establish the external threat level.
Yeah, exactly. He has to model the physical environment this cottage is going to endure.
Right. So in the software, he sets the location parameters to Riv, which auto-populates specific climate metrics.
And the big one the text highlights here is a design outdoor temperature of negative 21 degrees Celsius.
Okay, wait, let me stop you right there. Why does the software use negative 21 degrees?
Well,
Because surely Rivnen has had days colder than that, right?
Yeah.
Why not design for the absolute worst-case scenario on record?
that's a great question. So that specific metric, the design outdoor temperature, it's dictated by established building climatology standards.
Okay.
The document actually cites a specific standard, DSTUN B.1.127.20 ton.
Rolls right off the tongue.
Right. But the methodology behind that standard reveals a lot about modern engineering constraints. Negative 21 degrees isn't the absolute historic low.
Okay, so what is it?
It's the calculated average for the coldest 5-day period.
Which, I mean, that feels somewhat counterintuitive if you are trying to protect a house from freezing.
How so?
Well, engineering for a sustained 5-day freeze makes sense as a baseline, sure, but ignoring the absolute historical record leaves this perceived vulnerability, you know? Like, if the region has been known to hit negative 30 degrees during a freak overnight polar vortex, it seems super risky to intentionally cap your system at negative 21.
I get that. But it really comes down to the physics of thermal mass and, honestly, the economics of scale.
Okay, explain that.
Well, a house is not a tent. It's a heavy structure made of brick, concrete, insulation, timber.
Right.
So it has massive thermal inertia. A freak overnight drop to negative 30 degrees won't instantly penetrate the building envelope.
Oh, I see. The stored heat within the structure's mass will kind of carry it through a short-term anomaly.
Exactly. The 5-day period is the metric, because that is the threshold where a sustained deep freeze finally overcomes that thermal inertia.
And begins aggressively sapping the interior heat.
Right. And if you engineered the system to fight a once-in-a-century negative 30-degree event indefinitely, you'd settle the house with massively oversized infrastructure.
Oh, yeah. You'd need industrial-scale boilers, thicker piping,
high-capacity radiators.
Okay.
And all of that would short-cycle and operate terribly inefficiently during the other 99% of the winter.
That makes total sense. So Vassal is designing for the sustained stress test, relying on the house's own physical mass to bridge the gap during those extreme short-lived drops.
Precisely. And the software also requires Vassal to input the immediate microclimate surrounding the cottage.
Right. The text specifies this house is situated in a built-up area with generally favorable wind conditions and normal thermal protection.
Yeah, and that built-up area designation, it drastically changes the thermodynamics.
It is the wind, right?
Exactly. A house sitting on an open plain takes the full, unbroken kinetic force of winter winds. That aggressively strips heat away from the exterior walls through forced convection.
But tucking this cottage into a neighborhood creates a boundary layer.
Yes. The surrounding buildings break up the wind patterns, which lowers the convective heat loss the system has to compensate for.
Okay, so with the external threat modeled, the methodology shifts inward, right? To the generation and distribution of the heat itself, the blood of the system.
Right. And the system being designed here is convection only.
Meaning no underfloor radiant heating grids, just radiators.
Exactly. The entire thermal load is shouldered by radiators, and the operational parameters for the water flowing through the system are intense.
Yeah, looking at the heating devices tab, Vassal specifies a supply temperature of 80 degrees Celsius and a return temperature of 60 degrees.
That 20-degree delta T is basically the engine of the whole system.
Right, the water leaves the boiler at 80 degrees, travels to the radiator, and dumps 20 degrees of thermal energy into the air molecules of the room.
And then returns at 60 degrees to be reheated.
To make that happen, Vassal is specifying some very specific hardware. He's using steel panel radiators, the P-Ermo Ventil compact line, specifically fitted with Oventrop thermostatic valves. And the software imposes a critical physical constraint here. It limits the maximum length of these radiators to 1.2 meters and mandates they be placed against the outer walls with a location coefficient of 1.0.
Yeah, that location coefficient is a fascinating metric. The software is mathematically grading the efficiency of the radiator based on its physical placement in the room.
Oh, wow.
So a coefficient of 1.0 means a radiator is operating at peak theoretical efficiency because it's positioned directly under a window or along the coldest exterior wall.
Which makes sense. You put the heat source right at the point of maximum thermal vulnerability.
Right. When cold air bleeds through the glass of a window, it naturally drops.
So the 80-degree radiator creates a rising column of hot air that intersects that cold downdraft, neutralizing it before it can, pool on the floor and spread across the room.
Exactly. If you move that same radiator to an interior hallway wall, the software would lower the coefficient because you'd be fighting the room's natural convection currents.
That's brilliant. And the distribution network feeding those radiators is just as deliberate. The text outlines a radial or manifold distribution system.
Yes, and the way that 80-degree water travels is entirely decentralized.
Right. Instead of a traditional loop system where water just flows from room to room, losing heat along the way, this setup relies on a surface-mounted central cabinet, the SWNOP.
Yeah, I like to think of this central manifold less like a Wi-Fi router broadcasting a general signal, and more like a hardwired Ethernet switch.
That's a great analogy. It sends a dedicated physical line of water directly to one specific radiator, and the text assumes an average run of 15 meters of pipe per device.
And that physical isolation of the lines is vital for pressure balancing. Vassal specifies KN therm polyethylene pipes, specifically PEXC type.
What does the C stand for?
It denotes electron beam cross-linking.
Oh, okay.
Which is a process that alters the molecular structure of the plastic so it won't degrade under constant thermal expansion and contraction.
Wow.
The text notes these pipes are rated to handle 90 degrees Celsius and 1.0 megapascal of pressure.
1.0 megapascal is roughly, 145 psi?
Yep.
That is highly pressurized, near boiling water shooting through the walls.
It really is.
And with the hardwired manifold setup, if the Oventrop valve in the bedroom closes because the room reached its target temperature, the manifold simply stops flow to that single pipe.
Exactly. It doesn't throttle the flow or spike the pressure for the radiators operating in the living room or the kitchen. The system dynamically isolates the load.
Which brings us to the human element of the software's modeling, because we move to the Rooms tab next. The system has to map all of this heavy infrastructure against the specific, localized needs of the occupants.
Right. When Vassal begins programming the individual rooms on the ground floor, Auditor SDG calculates the necessary thermal power based on vastly different baseline requirements.
Yeah, the ground floor tour in the source material really highlights the stark contrasts in these microclimates.
Okay.
Like, the living room is 32 square meters, features 2 outer walls, and has a facade that is over 20% glazing.
And massive windows mean massive heat loss.
Right. So the target temperature there is set at a cozy 20 degrees Celsius. But then by contrast, the garage is 12 square meters, has only 1 outer wall, and its target temperature is clamped down to just 12 degrees.
The starkest contrast, though, is definitely the bathroom.
Oh, yeah.
The target temperature there spikes to 24 degrees Celsius, and the hardware specified completely changes to accommodate this.
Right. The software rejects the standard Permo steel panel and selects a specialized towel warmer radiator.
Yep, with a maximum length of 0.8 meters and a specific bottom connection labeled FH.
Okay, so the FH connection is actually a critical design pivot.
Oh, yeah.
Yeah, it's a standard 50-millimeter pitch connection situated directly in the bottom middle of the radiator.
Okay.
In a standard steel panel, water often just flows in one side and out the other, but a towel warmer is built like a vertical ladder, right?
Right.
So the F connection forces the high-pressure water up a central baffle so it cascades down through the horizontal rungs evenly, rather than just short-circuiting across the bottom.
That's incredibly smart. And beyond the hardware shift, the temperature discrepancy between the garage at 12 degrees and the bathroom at 24 degrees, it really illustrates how the software is forced to model human psychological comfort.
Not just baseline survival.
Exactly. Thermal comfort is deeply tied to human vulnerability at any given moment.
Right, like in the garage, a human is likely transitional. You're wearing a coat, moving quickly, getting into a vehicle.
Yeah, the ambient air temperature can sit at 12 degrees because you bring your own insulation.
But a bathroom presents maximum vulnerability. You're stepping out of a shower, completely exposed, with water evaporating rapidly off your skin.
And that evaporation strips kinetic heat directly from your body.
Right, so to counteract that rapid heat loss, the ambient air must be superheated to 24 degrees just to maintain the perception of comfort.
It's fascinating. And the software manages these distinct requirements flawlessly on a flat 2D plane. But architecture operates in 3 dimensions.
And that introduces anomalies that the computer struggles to parse automatically.
Yes. The document highlights a great example with room 4, the staircase.
Yeah, so the floor plan dimensions for the staircase landing are only 4 square meters.
Right.
If the software were strictly calculating floor area, it would assign a tiny radiator, assume the space is fine, and move on.
But Vassel has to manually input a ceiling height of 6 meters for this specific zone.
Because the staircase is essentially a vertical shaft cutting through the thermal boundaries of the house floors.
Exactly. This triggers a fundamental shift in the thermodynamics.
The system isn't heating a flat plane anymore.
No, it has to deal with the stack effect. Heat naturally rises.
Right.
So if you only provide enough thermal energy to cover a 4 square meter floor, that heat will immediately draft up the 6-meter vertical column.
Pooling at the ceiling of the second floor and leaving the ground floor landing completely freezing.
Precisely. So the software shifts from a 2D area calculation to a 3D volumetric calculation, significantly upsizing the thermal load required to saturate that entire vertical column of air.
It's a prime example of where flat architectural blueprints just fail to convey thermodynamic reality.
Yep.
The software compensates for the volume, but it relies entirely on the engineer to flag the structural anomaly.
And there are moments detailed in the text where the architecture actively breaks the software's automated logic.
Oh, the hallway glitch. This is easily the most revealing part of the document regarding the limitations of automated engineering.
For sure.
So room 2 is the ground floor hallway. It measures 6.8 square meters, and Vassel inputs the standard target of 20 degrees Celsius.
Standard stuff.
Right. But crucially, this hallway is entirely landlocked. It is situated dead in the center of the floor plan with 0 outer walls.
And when Vassel inputs those parameters, the software throws an error. A yellow warning bar flags the room.
The algorithm panics.
It really does. Auditor SDG's automated logic is hard-coded to optimize placement. It mandates that a radiator must be positioned against an outer wall to neutralize cold drafts.
But because there is no outer wall, the software cannot complete its primary directive.
Exactly. The default hardware simply does not fit the programmatic rules of a completely trapped room.
So it lacks spatial context. It basically requires Vassel to manually take the wheel.
Yeah, he has to override the system's automated choice and force it to accept a much shorter 300 millimeter high radiator, a CV30 model, specifically.
Okay, so the manual input clears the yellow error bar, allowing the system design to proceed.
Right.
But the text explicitly notes the consequence of this override. This manual selection leaves a 6% deficit in thermal power for that hallway. The radiator he forced into the design is mathematically underpowered for the cubic volume of the room.
It is.
Wait, accepting a known failure rate in a commercial proposal seems incredibly risky, doesn't it?
It does sound bad.
Like, if my phone battery is 6% short, it dies. If an aerospace engineer accepts a 6% deficit in fuel capacity, the plane doesn't reach its destination.
Right.
So if my heating system is 6% short, am I going to be freezing in the hallway?
Well, no. The source text provides the justification for this, and it really splits into two distinct realities of modern HVAC design.
Okay, what's the first reality?
The first is the limitation of the tool itself. The document explicitly states that Auditor SDG 2.0 is engineered for rapid approximate selections.
Okay.
It is an estimation tool designed to quickly generate a commercial proposal for cottages and townhouses. It allows a contractor to build a highly accurate budget.
But it's not the final word.
Exactly. For rigorous, down to the decimal thermal modeling, engineers export these designs into much heavier analytical programs like OZC and CO.
So Auditor SDG is the heavy, blunt instrument used to get the contract signed, not the finalized thermodynamic blueprint.
Right. But the second reality is purely physics. The software flagged the 6% deficit because it calculates the hallway in total isolation.
It treats the interior walls of that hallway as absolute thermal barriers.
Which is an architectural fiction. Drywall is an incredibly poor insulator.
Exactly the opposite of an exterior wall.
Yes.
That trapped hallway is completely surrounded by the living room, the kitchen, the bedrooms, and all of those are successfully pumping 20 to 24 degrees of heat into their respective spaces.
And heat energy aggressively seeks equilibrium.
Right, it does not respect property lines drawn on a floor plan.
Exactly. The excess thermal kinetic energy from the bathroom and the living room will bleed straight through the interior doors and drywall into the hallway.
So the human engineer understands the holistic ecosystem of the house.
Yes. A 6% thermal deficit on an isolated exterior corner room would result in a freezing space. But a 6% deficit in a landlocked, centralized hallway is easily mitigated by ambient thermal bridging from the adjacent zones.
Vassel ignores the software's warning because he knows the house will naturally balance the equation.
Exactly. It perfectly illustrates why specialized software hasn't entirely replaced human engineers.
Because the program is rigidly adhering to its logic gates, but the engineer understands how the physical house breathes and bleeds energy.
And that dynamic between static calculations and physical reality is really the ultimate takeaway from this whole exercise.
It really is. So just to recap for everyone, we started with the raw, freezing negative 21-degree climate of Rivne,
Right.
channeled 80-degree water through specialized polyethylene pipes, adjusted for 6-meter staircases and 24-degree bathrooms.
And learned when to let the software do the math and when human intuition needs to override a glitch.
Everything Vassel built in this simulation, the manifold routing, the staircase compensation, the manual override for the hallway, it's fundamentally static.
Yes, he is designing a fixed response to a historical 5-day climate average.
Right. Once those KN therm pipes are locked behind the drywall and the concrete is poured, the system cannot change its underlying architecture. It can only turn the valves on and off.
But the environment it operates in is becoming increasingly volatile.
Yeah.
We are moving away from predictable historical averages. As the external climate becomes more erratic, relying on a static, pre-calculated model from a piece of software used once during the design phase, it seems increasingly archaic.
It really does, which points toward a massive shift in how we manage building infrastructure.
Absolutely.
We are rapidly approaching an era where software like Auditor SDG isn't just an estimation tool used by an engineer before the drywall goes up.
Right.
Instead, an evolution of this thermodynamic modeling will live natively inside the house's architecture as an active AI.
Exactly. Think about a system that doesn't just rely on a thermostat's crude air temperature reading, but actively recalculates the required 20-degree temperature drops and dynamic manifold pressure routing minute by minute.
Wow.
A house that anticipates an unseasonal drop in wind chill, shifts the thermal load away from the unoccupied garage, and preemptively routes maximum flow to the living room's exterior walls before the cold even penetrates the glass.
A living system that actively fights the winter in real time, rather than just executing a mathematical playbook written a decade prior.
Exactly.
So the next time you step inside from a freezing wind and your home perfectly envelops you in warmth, you can appreciate the invisible math.
There's a lot going on behind the walls.
Right now, it's a static grid of highly pressurized polyethylene and meticulously calculated heat drops keeping you comfortable. But soon, the house won't just be executing a blueprint. It will be actively strategizing to keep you warm.